This is the last screencast for Chapter 4, and the main focus will be on what is called two-body problems. In other words, there are two objects that are connected somehow, and as a result, what is often the case is we will be able to generate two equations, at least, from each of the two bodies that are connected. And we'll show you several different ways that you can solve these kinds of problems. The first problem is what is called Atwood's machine. This was lab 10 in the physics curriculum, at least in my school. And Atwood's machine consists of two masses connected by a string or twine draped over a pulley that is free to rotate. We're going to ignore the friction in the pulley, and we're going to assume that the string or twine cannot stretch and is not going to break. And with those stipulations in place, let's assume that this object is going to accelerate in this direction, which means that mass number 1 is going to accelerate upward, mass number 2 is going to accelerate downward. And that is because mass number 2 is greater than mass number 1. Now, if you're thinking ahead and drawing some good logical conclusions already, I hope you can anticipate that the force of tension in this part of the string and the force of tension on the right side holding mass 2 in place, that those two forces of tension cannot be anything but equal to each other. You can't have a rope, whether it's across a pulley or not, that has different tensions in one part of the rope than the other. Either the rope will get all bunched up or the rope will break if the tensions are different. Another thing that you should observe or anticipate is that the acceleration A1 of mass number 1 on the way up should equal acceleration A2 for mass number 2 on the way down. Because if they had different accelerations, then either, again, the twine, the string will get all bunched up, or the string is going to snap. So the tension has to be constant all the way through, and I like to write tension as the force of tension, and the acceleration for both objects should be the same. Now, having said this, let's go ahead and draw two free body diagrams, one for mass 1 and one for mass 2. When we draw the free body diagram for mass 1, and again, I like to use F sub t, we have the force of tension acting up on mass 1, and we have the force of weight. Sometimes we use F sub g for the force due to gravity. Sometimes your book just uses W. Here we're talking about mass 1 times gravity. That vector represents the weight of mass 1 acting down. Now notice that the force of tension acting up is greater, this one, is greater than the weight acting down. And that's because it's accelerating. Remember, you have unbalanced forces. And if there is a net unbalanced force, that's what causes acceleration. And you recall that that is Newton's second law, F equals ma, where F is your net unbalanced force acting on a mass, and as a result, that mass accelerates. And technically, I should use a here as opposed to a G, because we're talking generically about acceleration, even though in this case it might be, you could have, sometimes we do have a specific acceleration like the acceleration due to gravity. All right, so when we look at the object on the right side, mass number 2, it also has a force of tension acting up, and it also has a force of weight acting down, which is different because mass 2 is greater than mass 1. Several things you should notice here is that the tension vector for mass 1 and the tension vector for mass 2 are equal to each other, because you can't have different tensions in an inelastic cord. Your problem uses inextensible cord, which is a word you might not have seen before. You should also notice that when it comes to the force of weight, we made this force of weight for mass 2 bigger than the force of weight for mass 1, because mass 2 has a greater mass. Now, having said that, you'll notice we have two equations that we can generate from these two masses, these two free body diagrams. The first one, the first observation is that the summation of the forces in the x direction for either mass equals 0, because the objects are not moving left and right. So we can kind of ignore those, and I'm going to erase them as a way of ignoring them. Now, when we look at mass number 1, we can see that the bigger force, which is going to be the force of tension acting up, minus the smaller force, which is the force of weight for mass 1 acting down, that creates an unbalanced force. And unbalanced forces equal ma. And we can further elaborate that this is the force of tension minus mass 1 times g equals mass 1 times a. And that's the equation that we have right here, just using my nomenclature instead of the book's. Now, if we look at the second mass, mass number 2, the bigger mass is the mass of weight for M2, the bigger force, I should say, minus the smaller force, which is the force of tension, which again equals ma, because it's an unbalanced force. And the mass of weight is mass 2 times g minus the force of tension, which equals mass 2 times g. And so there's my second equation right here. And both of these are the result of saying that the summation of the forces acting in the y direction for M1 and for M2 does not equal 0, so therefore it equals ma. You only have those two options. It equals 0, which means that it's at equilibrium, or it means it is not accelerating, the velocity is constant, or it equals ma, which means it is acceleration. So there we've generated our two equations. Now you should also know that we can solve these equations, and this is exactly what you did in Lab 10, Atwood's machine. You solve these two equations for the acceleration, which is the same for both, but in opposite directions. And you can also solve these two equations for the tension. Notice that the solution for acceleration does not have tension in it, and the solution for tension does not have the acceleration in it. So we have these two equations that fall out from the previous two. And now it's a matter of plugging in your numbers. Now there is something that is called the systems approach. And to be honest, I don't think I've ever used the systems approach. I kind of like the force diagrams the best. One of the things about the system approach is you only use those forces which are external, outside acting on the 2 or 3 or 4 or 10, however many masses that are connected together. These are forces acting from the outside on. They're forces that are external, not internal to the system. Now, as a result, that means forces that are internal can't be determined using the system approach. So you can use this for 2-body, 3-body, or more body kinds of problems. And we'll come back to that in a minute, but let's take a look at another 2-body problem. In this case, we have a mass, and I'm going to blow this up, that is on a horizontal surface, and there's a string connected to it. Here's a string connected to it. It drapes over a pulley and comes down and is connected to a mass. And the mass of the block, M1, is different than the mass of the object hanging at the end of the twine that is hanging over the edge of the table. That mass is different. Now, in this problem, we could begin with a problem where you have no friction. If there is no force of friction, then you're going to have an unbalanced force that's simply going to be m1 times the acceleration to the right, because there's nothing to get in its way. In this problem, and I'm going to erase that because this is not what this problem is about. In this problem, we do have friction. So I'm going to have my force of friction, and I like F sub F acting towards the left. We're talking about kinetic friction. We're going to ignore the little nudge you got to give it in order to overcome static friction. And pulling it in the opposite direction is the force of tension. And you'll notice that the force of tension arrow is bigger than the force of friction arrow because of the fact it's accelerating to the right, per the comments in the problem, in the text of the problem. Now, we can also look at what's going on vertically. And we have the normal force acting up, F sub n, I like to call it, and then we have the force of weight acting down. Now, you should be able to see that in this problem, the summation of the forces in the y direction equals 0, which is another way of saying the force up, F sub n, equals the force down, F sub w. And you may think that that is not important. And what you need to keep in mind is every time we have friction, we have mu equals the force of friction over the normal force, which therefore means the force of friction equals mu times the normal force. And in this particular problem, because there are no other vertical forces, that means the force of friction equals mu times the force of weight, because of the fact that there are no other forces acting vertically, and the normal force equals the force of weight. So this would be, I'm going to erase that and redraw it. So we can say that my force of friction equals mu times the force of weight, and then we can further break it down. The force of friction equals mu times m1g. And that may come in handy, that particular equation right there. So that is in the vertical direction. Now the summation of the forces in the x direction horizontally do not equal 0 because it's accelerating, meaning there's an unbalanced force. And this unbalanced force in the x direction therefore must equal the only alternative, which is ma. And therefore we can say that the bigger force, which is going to be the force of tension, here's my force of tension, your book uses capital T, is bigger than the force of friction, and your book uses lowercase f. That has to equal ma. And again, your force of friction can also be determined by using this equation right there. That can come in handy. So this equation is the result of this looking at the x direction, and this equation over here is a result of looking at the forces in the y direction. Now let's come down to the second body, mass number 2. It also has a force of tension acting up, F sub t, as you can see in the picture, and it has a greater force acting down, the force of weight, or you could say the force due to gravity, or you could just say lower small w like the book sometimes does, and of course that's going to equal m2g. And you'll notice several things. That the force of tension vector here and the force of tension vector here should be drawn to the same length because the force of tension cannot change. Let me fix that again. I don't mean here. The force of tension we're talking about is right here, this force of tension. Those two forces of tension, those vector lengths should be the same. Now, once again, we can talk about the summation of the forces. In this case, in the x direction is going to equal 0 because there aren't any going this way or this way. There's none in the x direction. But as far as the summation of the forces in the y direction are concerned, that must equal ma because it's accelerating downward. So we take the bigger force, which is the force of weight, minus a smaller force, which is the force of tension. This has to equal ma. And we can break up the force of weight into mass 2 times gravity minus the force of tension equals mass 2 times acceleration. And there's another equation that we've just generated. So with this information in hand, you can now plug in your numbers and you can determine what is the force of tension, and you can also determine what is the acceleration. And that's what the problem does. Now, if we were taking a systems approach, we would look at the entire system, which is made up of two masses. We ignore the mass of the string between them, and we can take those two masses times their acceleration, and they equal the unbalanced force. So, in a sense, my unbalanced force, the bigger force, the force of weight, minus this smaller force externally, which is the force of friction. Notice that this is acting on mass 2, this is acting on mass 1. Remember, this is a system approach, so we're talking only about the forces acting on the system. And it's the force of friction that's holding back the system, and it's the weight number 2 that is pulling the system and causing it to accelerate. So I have my bigger force right here minus my smaller force equals ma. And now I plug my numbers in, or I could solve this for acceleration right here. And I can determine the acceleration, but I cannot determine the tension because the string is part of the system. And the system approach only analyzes the forces acting from the outside on the system. The system is the string plus the two blocks. All right, coming over to two blocks in a chord. Now, I don't see this kind of problem very often in physics, but let's imagine that we have one block sitting on top of another block, and let's imagine that the bigger block is on a frictionless surface. It says that right here. So this surface has no friction. That's, of course, is very idealistic. And then the other surface is the surface between the smaller block and the bigger block right there. And that does have friction. And we're talking about a static friction here. And the question says, if we begin to pull on a string attached to the smaller block that is sitting on top of the bigger one, and we begin to pull on that, at some point, that pull will exceed the force of static friction and cause the upper block and the lower block to begin to accelerate to the right. Because the one block on the top is sort of connected to the bigger block on the bottom by friction, and the bigger block is on a frictionless surface, this whole thing is going to begin to move to the right. So, and this is a steady pull, not a sudden jerk, by the way, in which case inertia would take over. And what I've tried to do here with some of the writing, I'm going to try to move this out of the way if I can. It's not letting me do that, but Let's come down here. All I try to do is to explain where the terminology, where all the different equations come from. And again, they're coming from looking at the summation of forces in the x direction and the summation of the forces in the y direction for the block on top. And then we look at the summation of forces for the block on the bottom. And then we basically do algebraic substitution. And again, it can be kind of confusing. Either I'm the one confusing you because I like to designate everything as F sub T for force of tension, F sub friction, and force of weight and stuff like that, when your book uses different symbols. Whatever works for you, all they're doing is they're analyzing the bigger forces minus the smaller forces. And then they're substituting other values in. And you can see here where your unbalanced forces, the bigger minus the smaller equals ma. You can see that all over the place. All right, and I think I'm going to stop with the screencast there, and hopefully that gives you some important information to think about, as well as the necessary tools for solving problems of this nature.